everyone. My name is Min. I'm a core developer from the Near protocol, and I help develop Sharding. So if you don't know about Near already, first you should go check it out. Second, we are a proof-of-stake, fully sharded, and user-friendly blockchain. And this is why I'm here to talk to you about today, about sharding, how it works in general, and how we implement it at Near. Before we delve into any technical details, let's first talk about what sharding is and why we think it's important. Sharding refers to the partitioning of data and processing. In a sharded blockchain, we divide the whole account space into multiple shards, and each shard only processes transactions and store data for its own shard. So transactions from different shards can be processed in parallel to each other. In a way, this is similar to dividing a one-lane traffic into a multi-lane traffic. By doing so, we can increase both the speed and the throughput of the system. And to talk about why sharding is important, I want to first mention something called the Scalability Trilemma. Some of you might have already know it. It's like a concept first brought up by Vitalik. And it says it's very hard for any blockchain to achieve all of the three properties: scalability, decentralization, and security. In a traditional non-sharded blockchain, every node in the blockchain has to process all transactions and store data for the whole chain. So the performance of the whole blockchain, no matter how many machines there are, is still limited by the performance of every single machine. So if you want to make the blockchain process more transactions faster, we can either use better algorithms or optimize our code, but ultimately, the physical processing limit of the whole chain is still limited by the physical processing limit of every single machine. So to make the blockchain faster, we can either make every node in the system run on better machines, which will make the blockchain less accessible and less decentralized because we're increasing the entry barrier for anyone to run a node and join the network. Or we can offload some of the processing off-chain by using layer 2 solutions. But then we divide the part of on-chain and off-chain security, and we risk attacks that's specifically targeting on the off-chain component, which is not safeguarded by on-chain security. Now, sharding solved this trilemma by not requiring every node to process all transactions and do all the work by themselves, by spreading the load among different shards. So the more shards we have in a system, the more processing power we have in the blockchain. So the blockchain becomes scalable. It is also more decentralized because we're not requiring everybody to run on super high-performance machines. And ideally, we can run a node with just a personal laptop. And lastly, our blockchain is as secure because each shard in the blockchain is still safeguarded by the whole chain. So every shard is as secure as the whole blockchain. Okay, now you might be wondering, how is this still a trilemma if there exists a readily available solution already? And here's the catch. There's no free lunch in the world, right? So the cost we have to pay for sharding is its complexity. Comparing to a non-sharded blockchain, a sharded blockchain has more horsepower. It's more powerful. It's more faster. It can process more transactions. But it's also much more complex to build. And to make it right, we have to solve a lot of challenges. And some of these challenges, as you will see, will impact developer experience or user experience directly. And some of these challenges will make the internal implementation of the blockchain harder. And this is what I'm here to talk to you about for the rest of this presentation. What are these kind of, what these challenges are and how we at NEAR are going to solve these challenges. But before that, let me first give you a very high-level overview for NEAR's sharding approach. At NEAR, with sharding, we still only have one chain, and the chain produces one block at a time. And this block itself doesn't include any actual transactions. Sharding is implemented through a concept called chunks. So each chunk includes transactions from each shard. So in a way, chunks for each shard is similar to blocks in a non-sharded blockchain. Blocks and chunks are produced separately, but blocks contain chunks by storing chunk headers as part of the block content. Note here, not the full chunk, just the chunk header. So our block is scalable to the number of shards in the system, right? And every block can contain one chunk from each shard. And now we're ready to talk about the first challenge, and that is cross-shard transactions. So cross-shard transactions are transactions that involve accounts on different shards. Think about this simple example. Alice wants to send 10 NEAR to Bob, but Alice's account is at shard 0, and Bob's account is at shard 1. And here's how this transaction will be processed at NEAR. At first, this transaction will be sent to shard 0, where Alice's account is at. And shard 0, the machines in shard 0 will verify Alice's signature on this transaction and charges Alice's account by 10 NEAR and convert this transaction into something we call a receipt. Now, shard 0 has done everything it can regarding to this transaction, and the rest of the work has to be done by shard 1. So shard 0 will send this transaction to shard 1, this receipt to shard 1, and the receipt will be included as part of the next block. So when shard 1 process the next block, we'll see this receipt and put 10 NEAR to Bob's account. And this is the end of this transaction. So I want to talk about how this transaction is processed here at NEAR comparing to how it would have been processed in a non-sharded blockchain. So first, you'll notice that this transaction is actually processed in 2 blocks, not 1 block, right? And second, in theory and in practice, there could be another transaction that comes in, also included as part of the second block, and it also changes Alice's account state. And this will actually happen even before the first transaction is completely finished. So in other words, this transaction is actually processed asynchronously at NEAR. In a non-sharded blockchain, transactions are processed sequentially, one at a time. The next transaction won't start before the previous one is finished. However, at NEAR, transactions are processed asynchronously. That means transactions, they can actually overlap with each other. And 2 transactions, they can modify the same account state even before each other is finished. So that means developers, they have to write their contracts in a way that is safe to be accessed concurrently. Now, concurrent processing or concurrent programming is not something easy, right? Especially for developer from a Web 2 background. So this is definitely not ideal. It adds a lot of complexity and difficulty to that experience. And that is something we are actively working on. Like we're thinking about adding synchronous support for synchronous transaction processing in our blockchain. But like this asynchronous nature is what happens behind the scene, right? And if a developer wants to truly realize the high performance brought up by this by a sharded blockchain, this asynchronous processing is, at least for now, unavoidable. And that is the first challenge. The second challenge I want to talk about is related to security. In a sharded system, a sharded blockchain, transactions are no longer verified by all validators in the blockchain. They're only verified by validators in each shard. So it is possible for a malicious actor to gain control in the majority of validators in a single shard without having more than 50% of total stakes in the whole system. And that is called single shard takeover. And this is a serious problem because if one shard becomes invalid, the invalid state, other shards can actually be corrupted too, because invalid state can travel from one shard to another via cross-shard transactions. And note here, like this, the other shards, the validators in the other shards, they can all be honest. But other shards can still be corrupted too, because the state of the other shard could depend on the state of this corrupted shard. To solve this problem, one solution that we use at Near is by randomly assigning validators to individual shards at the beginning of something we call an epoch. And an epoch is a duration of time or blocks that approximately last for 12 hours. So about every 12 hours, we reshuffle our validators and assign them to different shards. And because in this randomized assignment, validators cannot control which shards they are assigned to. So it's very hard for them to coordinate with each other to be assigned to the same shard. So in fact, the probability that the single shard takeover happens decreases exponentially to the number of validators in a single shard. So if we have enough validators in every shard, the probability can be very, very small, like 10 to the negative 26, and negligible. However, that is only a partial solution. And the reason for that is this shard assignment information is actually public, and it's released at the beginning of every epoch, right? So during this duration of every epoch, an adaptive attacker could actually take this information and deliberately choose a shard to bribe and corrupt. And the more shards there are in this blockchain, the easier or the less resource it needs for this adaptive attack to happen. Again, there's multiple solutions to this problem, and one solution we use at Near is called Fisherman. A fisherman can be any node in the system. They don't need to be validators. In fact, they don't even need to announce their roles in advance. So there's no way for the malicious attacker to know all of their existence and contact each one of them and bribe all of them. So when a fisherman sees an invalid transaction, it will create a message called a challenge, which will include a proof for why this transaction is invalid. And it will then broadcast this challenge message to the whole network, including every validators, including validators in other shards. And when the other validators see this challenge, they need to verify whether it is true or not, because Fisherman itself could be malicious too, right? So, and here's the beauty of this algorithm. Here's the magic. This challenge, the proof included in the challenge, can be verified without the original state of the original shard. So even the validators that track other shards, not the original shard, they can verify this challenge very quickly without needing to download the whole state of that shard. And after the validators verify this challenge, they will slash the malicious validators, take away their stakes, and revert all blocks happening after the invalid block, and restore the blockchain state back to a valid state. So with this Fisherman technology, if there is at least one honest node, not validator, honest node tracking each shard, the whole system will be secure. However, this is still only a partial solution. There's one subtle but important requirement for this Fisherman technique to work, and that is any node must be able to see the full content of a chunk in order to verify or challenge it. And remember when I said it before, each block only include chunk headers. They don't actually include the whole, like the full content of a chunk. So it is possible for a malicious chunk producer to produce a chunk and only publish the chunk header to be included in a block and withhold the full content of the chunk. So there's no way for other nodes, other validators, or non-validators in the system to verify whether the chunk content is valid or not. And this is called the data availability problem. The solution we use to solve the data availability problem, we use something called erasure code. And erasure code is an algorithm that split a full piece of data into multiple parts. So the original data can be reconstructed from only a subset of these parts. So when a chunk is first produced at a near blockchain, the chunk producer, the validator who is responsible for producing this chunk, has to divide this chunk into multiple parts using erasure code. And there are equal number of chunks to number of validators in the system. So this chunk parts will be distributed to all validators, one for each validator. And when validators seize the block that contained the chunk, they will only sign on this block if they have received their own chunk parts. So if the block is signed by the majority of validators in a system, that is more than half of the validators in a system, and we assume there are less than 1/3 of malicious validators. That's like a common assumption we usually make in blockchain. That means there are at least 1/6 of validators who have signed on this block and have received their chunk parts. So when another node wants to request the original chunk, they only need to gather these chunk parts from these validators, and the original chunk content can be recovered. And that is because of the way how erasure code works. As a TLDR, the power of a sharded blockchain comes from the fact that not every node doesn't need to process all the work, doesn't need to process all transactions, and they spread the work to other nodes, right? But there's a problem with that because they don't do all the work. They have to be able to trust the work done by others. So we have to build these additional technologies like Fisherman or data availability to ensure that this trust is not being abused. As a final recap, sharding is a very powerful technology. It is very simple, but can be very complicated to implement. And there's a lot of challenges we just described to be able to make it right. And we have to design it very carefully to avoid any problem happening to the whole ecosystem building on top of the blockchain. But at the end of the day, at NEAR, we strongly believe that sharding is essential to achieve the mass adoption of blockchain. And that is the goal for NEAR. Finally, I want to give you some updates on the sharding timeline at NEAR. Last year, we migrate our mainnet from 1 shard to 4 shards. And in fact, NEAR is the first blockchain that operates on multiple shards. And very soon this year, we're going to deliver chunk-only producer, which will increase the number of validators in the system and also decrease the cost or requirement for running one. And later this year, we're going to make our blockchain fully sharded. That means there's no need for any node in the system to track all shards. And sometime next year, we're going to enable dynamic resharding, where the different loads among different shards will be rebalanced automatically and dynamically on-chain according to live traffic. So the full power of sharding will be fully unlocked, and the near blockchain will become limitless. And that is the end of my talk. Unfortunately, do I still have time for questions? Okay, sorry. But here's some resources if you're interested in becoming a validator. Here's like some pages you can go to. If you want to try out Near, and we have, you can get a preloaded Near wallet and with your name at this address. And if you're a developer and you want to build an interesting project and earn some prize for that, you can also do that. Thank you.